Okay, I'm back. Bit of bonding. We talked about bonding in class the other week, but it is time to make a little podcast for you to revise with. So, thanks all working here. How do we join these things together? We've talked about elements, and elements are made of only one type of atom, so they're sort of pure, if you like, a pure substance. Atoms can then be joined together in three different ways to form compounds, and the smallest particle of a compound we call a molecule. And a molecule, in a sense of a compound, has a set formula. If you're making mixtures, then there's no set formula. There's a difference there. We're not going to talk about mixtures. We're more interested in compounds. So compounds can be ionic, and one atom steals electrons from another atom. And I won't put it in about the web, but we did discuss one local school as being a good model for ionic bonds. Whereas, of course, Woodleigh is a wonderful model for covalent bonds, where two or more atoms are shared by electrons. They share electrons. And of course, we've also talked about metallic bonds in passing, where electrons are able to move freely between atoms in a lattice of metal atoms. So we get this ability to conduct electricity and heat, the ability to bend them into shape and to draw them out into wires. We call that making wires ductile. If copper is very ductile, you can draw it out into thin wires. Metals obviously are easy to shape and form into jewellery and all sorts of wonderful things. And we call that malleability. But we're not too worried about metals, so we're going to worry more about ionic and covalent. Do we need to revise that in a hurry? No. You can go revise that in the other podcast. So, an ionic bond. So sodium has 11 electrons, 2 in its first shell, 8 in its second shell, and then there's 1 that lives a long way from the nucleus in its outermost shell. Chlorine has a different problem. It's got 17 electrons, 2 in the innermost shell, 8 in its second shell, 7 in its third shell, which means it's got a hole, it's got one space it could fill. So in the case of an ionic bond, chlorine, its nucleus has greater power to attract that electron away from the sodium, and so sodium gives up an electron to chlorine, and they become charged particles. So we now have a sodium ion, so it's positive, it's a cation, and a chlorine ion, which is negative, so it's an anion. Because now we have, if I could pause these, it'd be handy. I can't pause the thing. But here it has equal number of protons and electrons, and it gives up an electron, so it's got more positive charges. It had equal number of protons and electrons. It's now gained an electron, so it's now got an extra negative charge, hence these symbols plus and minus. And I've just talked all the way through that slide, so I don't need to talk to you about that at all. Cations are obviously anyone that loses electrons. So if you lose one electron in this first group, so hydrogen, sodium, potassium, silver, and copper will all give up one electron. That one electron in the outermost shell, there's obviously more as well. Magnesium, calcium, barium, zinc, and copper can also give up. Copper is twice. Will give up 2 electrons. Metal's a little bit different. Boron, aluminium, chromium, and iron are capable of giving up 3 electrons. You tend to find them clumped together. And of course, do you know anything about these elements? They are all metals. So cations tend to be metallic. On the other side, we have the negatively charged anions, and these all tend to be non-metals. So sodium and phosphorus, can give up 3, can gain 3. Oxygen and sulfur can gain 2. Fluorine, chlorine, bromine, and iodine, all below each other on the periodic table, will all gain 1 electron, and therefore have a negative charge of 1. In case of covalent bonds, everything's much more civilized. So in this form of bonding, we have a sharing of electrons. Hydrogen, of course, has 1 electron in its outermost shell, but needs 2 in that shell to be full. Carbon has 2 in the inner shell, and then 4 in its second shell, which means it needs 4 to be full. So it can combine with 4 hydrogens and make methane, with everyone sharing electrons. So everyone's got a full outermost shell, everyone feels happy about things. These are much stronger bonds, generally, than the ionic bonds because of that stability that's created. But I've just done that, haven't I? So I'll keep going. And then, of course, the last group is this idea of the metallic bonds. And in metallic bonds, this lattice, attempt to make a lattice structure here. So the knobs are sort of nuclei, and all the electrons are attracted to a nuclei, obviously. But when you add energy, such as put a current through it, then it activates those electrons, and they're able to move around, and they freely move from one to the other, which means that electricity can pass through a metal. And heat's the same. Heat energy is the same. It can pass through that metal. And that's probably the last slide, I think. And that's how things join together. There we go. Done.